Electric circuits! Yay! No! So the objective of this week's lab is to be awesome, to understand circuit characteristics of resistors connected in series and in parallel, and to gain experience measuring current and voltage using a multimeter. Oh, he saw us. Oh, no, he's gonna get us. Current. Okay, so basically it's really important that when we're talking about characteristics that you know the proper language to use when describing these characteristics. So current is the flow of charge. The symbol we use to represent it is I. The units are amperes, represented by A. Now voltage is the electric potential energy difference, and it is given to us in volts. It's represented by the letter V. So if we have a flow of charge, we're going to imagine that to be water. And that's our current. And then our voltage is going to be the height of a waterfall that our current or our water would fall down. So just like we have a gravitational potential energy, our electric potential energy in our analogy will have greater potential to do work at a higher height. So higher height difference of our waterfall, greater voltage. Yay. Now resistance describes the wire's resistance to current flow. It's represented by R and given to us in ohms. So if we go ahead and stick with current as water flow, voltage is the height difference that our water goes down over a waterfall. Our resistance will be the incline of our waterfall. So if it's just like a cliff and there's water going over, there's no resistance. That water has no chance. But if there's a slight incline, then our water will have greater resistance. So current, voltage, and resistance all come together with Ohm's law. So what Ohm's law is saying is that the voltage drop across a resistor is equal to the current flowing through the resistor and the resistance of the resistor itself. Booyah! Okay, so now to see Ohm's law in its ninja form. Okay, so different types of circuits. One type of circuit that we will be using today will be a series. So you have resistors in series are connected from end to end. So you see here we've got current, voltage, battery, resistors. Awesomeness. Okay, so let's apply Ohm's law to resistors in series. So draw. So we've got our voltage battery, we've got current flowing through our circuit, and we've got the resistors 1, 2, and 3. Now what's really cool is we can say that if we want to find current, we can group these resistors together to one massive resistor, RS, R series, which is an equivalent resistance. But let's prove that. So we're going to say that V battery is equal to the voltage drop across resistor 1, 2, and 3. So we add those together, we break it down to Ohm's law where V is equal to IR for each of those. We pull out our current because our current's going to be the same throughout the entire thing, and we see that the resistance of all three of these resistors together is actually equal to RS. Yay! Now again, I just want to write out that our total current through is equal all the way through. So across resistor 1, 2, and 3, I. And then again, voltage is our V battery is equal to V1 plus V2 plus V3, where V1, V2, and V3 are the voltage drops across the three resistors that we have in our series. Yeah, V battery. Yeah, it's Batman. Batman battery. So sum of voltages is equal to V battery. That's the pretty language for it. So another type of circuit we'll be dealing with is a parallel circuit. So resistors are connected in parallel when the same voltage is applied to each resistor. So this image is in your book. It's showing current coming in and then it splitting off across three resistors. Okay? So, but you have to keep in mind that the same voltage will be applied to all resistors. So let's apply Ohm's law to to resistors in parallel. So we're going to go ahead and draw. This is a little bit different drawing, but it shows you that the same voltage is going in, and then once it hits that like dot, it's going to separate. And so, well, it's not going to separate, but it's going to hit all three resistors. And so we want to solve for I total. We want to solve for the current that's going through the system. And so we're going to go ahead and we're going to say that I total is equal to all of the different currents that go through those different resistors. And when we apply Ohm's law and solve for I, we'll get I equals V over R.
Now we know that all the voltages are going to be the same, so we have to account for the different resistances from the different resistors. So we go ahead and say that our total current is equal to I1 plus I2 plus I3, which is going to equal V over R1 plus V over R2 plus V over R3. And then we can pull out that V, and then we have 1 over R1 plus 1 over R2 plus 1 over R3. And so this will give us our Ohm's law awesomeness, but we also can see that RP, we can have this equivalent resistance, but for a parallel system, it's going to be 1 over RP, because our equivalent resistance is going to be the inverse. We know that our total current is going to be equal to the currents that encounter each resistor, and that our voltage will be, V battery will be equal throughout the entire system.
Yes, good times. Now let's talk about how to look at our resistors. Now there's a color band, there's different color bands on our resistor that allow us to calculate the total resistance of our resistors. So let's identify these as A, B, C, and D. And if you look in your lab manual, on page 7, you'll see this little color code. And so the first A is going to be our first digit, B will be our second digit, C will be the number that we multiply by, and D will be our tolerance, which is awesome and great, and we don't really care about it in this lab. So once we multiply that out, we get 2.5 times 10 to the 7 ohms. So basically what that's saying is this resistor is saying, you shall not pass. The end. That was a lot of information, very quickly. If you have any questions, go ahead and email your instructor or talk to your TAs because they're rocking awesome. Everybody's having a good week. Watch out for dinosaurs. They're scary. They even eat Vader. Oh.